Let's talk about bisectors and triangles. This is the second video for week 3 of Geometry 1A, Unit 3. So again, talking about bisectors and triangles and using properties of perpendicular bisectors and angle bisectors as we go through our lesson today. So we need to refresh our memory a little bit before we get into our theorems, so let's look over the definition of equidistant points. So if I have this image here, I would know that point D is equidistant from points B and C if and only if I measured BD and it was equal to the measure of DC. And hopefully this is pretty intuitive. So, it's kind of obvious that if I have a point D and it's just as far from point B as it is from point C, then that distance is equal. So point D is equidistant or equally distant from B and C if and only if BD equals DC. We also need to review the definition of perpendicular bisector of a triangle. So a line, array, or a segment that is perpendicular to a side of the triangle at the midpoint of the side is a perpendicular bisector. Think about it by splitting the definition of perpendicular and bisector. So I think you could all identify for me if I gave you a line and I said, which of the following is perpendicular to this line, I think we could all pretty quickly identify that the middle dotted line, that this guy, is perpendicular to the line that I drew, right? And you can tell somewhat visually, but also because I put in that little right angle sign, right? You know that's what perpendicular means. And bisector, we talked about this last week. We know that a bisector splits, it could be a line, array, a segment, a point. It's something, but it splits, let's say we're dealing with a line segment, it splits it in half, right? So it splits into two segments of equal measure or two congruent segments, right? So combining those definitions, a perpendicular bisector would not only be a line, array, or a segment that is perpendicular to the segment in question, but also one that bisects it, right? So in this example, if I'm looking at this line segment AC, a perpendicular bisector must first of all be perpendicular, which you can see through this symbol that it is, and it must bisect, meaning it must pass through the midpoint of that line segment. Okay, beautiful. Let's continue. The perpendicular bisector theorem. So if a point lies on the perpendicular bisector of a segment, then that point is equidistant from the endpoints of the segment. So I won't over-explain perpendicular bisector because we just gave quite a bit of detail on that. So any point that lies on my perpendicular bisector is equidistant from the endpoints of the segment that is being bisected. So in this example, I've got this green line that's my perpendicular bisector, right? And it's bisecting line segment RS. And I can see that because I see that RM and MS are congruent, which means that M must be the midpoint of these two segments. And I can also see this perpendicularity symbol, right? So I've got this line that in green, that's my perpendicular bisector. And I'm saying any point on this line will be equally distant from the endpoints of my segment in blue, so R and S. So just as an example, let's look at like point T. If I measured TR and I measured ST, they would be equal. If I measured RV and I measured VS, they would be equal, and so on and so forth. And hopefully this seems, again, somewhat intuitive to you, but this is established by the perpendicular bisector theorem. And it's any point on the line. So I've only defined a couple points, but you could pick any random point along this line, measure its distance from R and from S, and those two distances would be equal. In other words, any point on the line on the perpendicular bisector is equidistant from the endpoints of the segment being bisected. That's the perpendicular bisector theorem. Okay, let's continue. there is a converse of the perpendicular bisector theorem. So we just talked about, being given a perpendicular bisector of some segment, we've been told what we can conclude about points on the line and their distance from the endpoints of the segment being bisected. The converse of that, what if we just start out with some point? What if we just start out with some point that's equidistant from the endpoints of a segment, right? So this was it's kind of like flipping the order, because before this is something we were making the conclusion about. For the converse, this is what we're starting with, right? So I've got this point H, and I'm saying it's equidistant from points F and G, which form a line segment. Well, then it stands to reason that this point H must lie on the perpendicular bisector of the segment. Okay? So again, the converse of the perpendicular bisector theorem tells me that if I have some point H that's equidistant to 2 points F and G form a line segment, then H must be on the perpendicular bisector of the segment. Okay? If you need to, take a moment to rewatch this section on perpendicular bisector theorem and the converse to keep them straight. All right? Another theorem regarding perpendicular bisectors, kind of building on the converse. So before we were talking about what happens if I've got a point that's equidistant to 2 points that form a line segment. What if I have 2 points? So I've got these 2 points and this segment, I've got points V and T and this segment RS, and I'm saying they're all on the same plane. So think of your computer screen as a plane. And I've got these 2 points, and I'm saying both of them are equidistant from the endpoints, right? I'm not saying V and T, I'm not saying anything about the relationship between them. I'm just saying that V is equidistant from R and S, and I am also saying that T is equidistant from R and S. I'm not making any claims about the distance between V and T. What I am claiming is if I have the situation going on where I've got a line segment and I've got 2 points, and each of these points are equidistant from the endpoints of that segment, then if I join them together, if I formed a line between them, then this line would be the perpendicular bisector of the segment. Okay? And again, hopefully this is somewhat visually easy to confirm. Let's go through it one more time. If I've got 2 points, in this case T and V, and I've got a line segment, in this case RS, and they're all on the same plane, and each of these 2 points, point T is equidistant from the endpoints R and S, point V is equidistant from the endpoints R and S, then if I form a line between these 2 points, this is the perpendicular bisector of the segment RS. Okay? Beautiful. So that's the last thing I wanted to discuss in this second part of the video. Again, I know that this theorem, at the converse, and the other theorem that I discussed, all are closely related. So it's step 1 is making sure you understand the material, but step 2, make sure you get the material straight and which conclusions and which criteria belong to which theorem. All right? I'll see you guys next time.